Hey everyone, so this is a video about this bicycle that I've made out of wood using CNC milling. I'm going to do a little intro about this bike and why it's special, and then I'm going to tell you a bunch of CNC tips because I found that a lot of the advice on the internet, it's either like really bad advice for beginners or it's advice from pros running professional level machines. Like if you're not running the equivalent of a Tormach as a beginner or you're using stepper motors, you're not gonna get like the same speeds and feeds or results as people who are running pro things, and I'll talk about that in detail. But first off, I'll just address the elephant in the room is I don't think anyone's gonna actually watch this video, and that's because everyone hates bicyclists. And even bicyclists hate other bicyclists. Like I've been biking for years now, and there's just a lot of toxicity. People will always hate on someone else for their gear choice, their wheel choice, just all kinds of things, and everyone hates a bicyclist in the road. So I don't fault you for closing out this video. Like if you are a bicyclist and you see this, you might even hate my design decisions. And if you're a CNC machinist and you see this, you might hate what I do. And if you're a woodworker, woodworkers don't think CNC machining for wood is real woodworking, so I don't care. I make YouTube videos because it's stuff that I think is cool, and if there's someone out there who's like me who also thinks it's cool, they'll hopefully find this video cool. And this bike is just an expression of myself. It's like everything I've wanted in a bike, and that you can't buy it. The closest thing is Hermes sells a mini Velo, and that's what this is. It has these small 20-inch wheels, and they're really popular in Japan and Europe, but they're pretty hard to find in America. You can buy a few, but your selection's really limited, and especially like if you want certain features. That's part of the reason I made this. Like, I wanted to have the straight line feature where the stem is in line with the top tube. You'll only find that in like TT bikes or maybe some track bikes. That's a really hard feature to find. I wanted pursuit bars with shifting. I know there's only one brake. I know it's dangerous. I don't care because it looks sick. To me, that is. I just wanted something that looks sick. It is a straight fork because I wanted the front tube to be in line with the fork. I'll talk about geometry later, and it's a 1X setup with a 9-speed derailleur because it was cheap, and it was what I had on my old mini Velo. So I've been riding mini Velos for, well, I was riding my one mini Velo for 7 years now, and the biggest advantage I felt for a mini Velo was you could fit it in the back of a sedan. So I drive a Honda Accord. You can stuff this in. You don't need a bike rack. And since it is a full-size frame with smaller wheels, you can have some of the handling of a road bike. But I found that the geometry of mini Velos was just so ugly. So to accommodate the smaller wheels and the shorter wheelbase, mini Velos, they tend to have rake offsets on the fork and also the rear chainstay. It'll angle downwards, and I just felt like that's so unaesthetic and so ugly. So for this bike, I went with super short cranks. I think these are 150 or 155, and that's to stop pedal strikes. With mini Velos, you are really close to the ground, and my chainstays are parallel with the ground, and I felt like that was such a purity of lines. I wanted to have the lines as clean as possible, so top tube is parallel with the ground, stem is parallel with the ground, bars, pursuit bars, parallel with the ground, and the chainstay is parallel with the grounds. I wanted to have as much unity in the lines as possible. All of the radiuses are the same. I wanted to have these chamfers flow into fillets. I wanted to have just really clean design, and yeah, that's why I made this bike. So you can tell it's made out of wood. I find that wood grain is one of the most beautiful, like, aesthetic things you can find. It has the feeling of nature, and if you do it correctly, you can make wood really strong. So underneath the wood is metal. I'm not sure you can see this, but there's aluminum right here that's visible. So all of the lugs and all of the parts that undergo the highest amount of force are made from aluminum, and the tubes inside of here are steel. So it's not a light bike by any means, but it is compact. And the wood is not actually just normal wood. This is stabilized wood. So I have a giant 5-gallon vacuum chamber. All of these pieces of wood that were milled were placed in that chamber with a plastic bag. Inside that bag was resin. Unfortunately, after stabilizing, some of the pieces did warp, so I didn't get perfect faces touching each other, but that's just one of the things that happens. So if you do plan on stabilizing wood at home, you have to know that when you bake it, or when resin cures, it may warp the wood a little bit. So the best thing to do would be like mill it, roughing pass, stabilize, and then finishing pass if you have the fixturing. Yeah, I think that's pretty much the essence of this bike. Another thing I noticed is like there's a lot of wooden bikes on YouTube, but there's very few people like making footage of them riding it. You don't really see people riding their wooden bikes much. So here's some footage of me riding the wooden bike.
She took me in and gave me breakfast. She said, "Do you come from a land down under, where women go and men wonder? Can't you hear the thunder? You better run, you better take cover."
So next up is CNC. How did I make this bike? So starting out, just one piece of this bike here, just one component, not even both sides, one sub piece would take about 4 hours, and that was ridiculous. And I was using these 1/8 inch DLC coated single flutes, and I got a lot of advice early on about CNC milling, and people often say you should start out with single flutes. They're great, they have good clearance for the chips, and another piece of advice was to have adaptive tool paths with constant tool engagement. So everything I was CNC milling, I was doing it with adaptive tool paths. And when I was at work, I noticed like the actual machinists, they weren't using adaptive tool paths. They were just straight up pocketing these operations in aluminum. And I was thinking to myself, well, if these are professionals and they're doing this, why did the internet tell me something different? And it's about theory versus practice. So in theory, if you can run adaptive tool paths, trochoidal tool paths that have constant engagement, and you have the feed, it is in theory better. You're using more of your sharp edges on the tool, you're going deeper, but in practice, just a traditional pocket is much faster for most cases, especially when you're using a hobby machine. So by hobby machine, I mean anything short of a 5-digit Tormac. So my machine is a Fox Alien Vasto. It has been upgraded with the closed loop steppers. It has a 1.5 kilowatt VFD spindle. And even that, it's just a hobby, it's just a toy. It's not a real CNC mill. And when you're looking at things like the Datron Neo 2, Datron Neo Cube, or pretty much many professional level milling machines, these are using servos and really, really thick ball screws. They have rigidity, they have speed. They're running 2 or 3 orders of magnitude faster at least. I know there's some tricks with the Datron that the working area is small and it's designed only for aluminum, but with a hobby machine that's running stepper motors, you'll never achieve the stiffness or the feed rate that's required to do adaptive milling. And just for example, if you're doing an adaptive, your travels have to be very fast because you have to go through you're doing air cutting, you're moving in between the trochoids, and you have to think about chip thinning. So radial chip thinning, if you're cutting and you're doing an adaptive toolpath and you're not getting in your radial load is not deep enough, your chip thinning is going to reduce that chip to nothing. And I can't explain chip thinning very well. I'd highly advise you watch other videos for chip thinning, but it really complicates the tool paths that you're going to run. And I can give you some advice right now, and you're not going to run into that problem if you just do some really stupid, simple stuff, which is what I did eventually to go from a four-hour tool path down to a half-hour tool path. So yeah, I started doing pocketing instead of adaptive operations, and instead of using these 1/8" end mills, I used thicker 1/4" end mills, and that was a huge difference. With the smaller end mills, I was getting tons of noise. They're flexible, and you can go deep, but there's a lot more chatter when you go deep. Switching to the thickest end mill that you can fit in your spindle, it really changes the audio, like the sound, the chatter, everything just is so much nicer. You can run these faster, harder, more aggressive. Thicker end mills are just the way to go. And I learned something really cool. You'll notice the end of this end mill is not coated. Here's one of the same end mills, also DLC coated. You can see the coating extends to the outside, and that's because I have this little jig that I can place my end mill in, and I can sharpen it with a diamond stone. And the most amazing thing about these single flutes is you can sharpen them without losing the rake angle. You just have to align that cutting edge to the top, make a little jig, and just sharpen it. And you can see just how much I've sharpened this one flute end mill. Probably 3 or 4 millimeters down. You can use these and get a lot of your money's worth if you just keep sharpening a single flute. But a single flute alone will not give you really fast CNC operations. So one thing that helped, I already mentioned, going to traditional pockets. The next thing people say is like, go more teeth. So I have a 2-flute compression, DLC coated, and I had very bad results with the 2-flute compression. So everyone says you get way less tear out, it's way better on the fibers, but this is a pretty long end mill, and I don't know if it was the length or anything else. I did download Millilyzer, which is a great software that analyzes cutting forces and helps predict milling. And it did predict with this end mill I would have good results, but I had very bad results with the compression 2-flute. I did have better results with 3 flutes, and Millilyzer, the graph showed that if you can get the cutting tip to cut into the material while the previous flute is engaged, the cutting force is lower. But that wasn't the silver bullet that I really wanted. The silver bullet was this end mill. I have a 3D printed end mill holder here for my most common end mills. And this, even though it's 3-flute, it's a roughing end mill. And I don't know why people don't talk about this enough. I don't know why there's not more YouTube videos about roughing end mills. The 3-flute roughing end mill alone lets you go from, obviously, if you have 3 flutes coming from the 1 flute, you can run it 3 times as fast with the same rotations per minute. If you increase your rotations per minute, you can go even faster. And these little chip breaker parts, these little, I don't know what to call serrations, they concentrate the force. So only half of the cutting flute edge is cutting at any given time, and that effectively halves the amount of torque required to cut through the material. And when your torque is reduced and your chips are very small, you can cut very fast. And I was astonished at how deep I was going with these. So with 3 flutes, 3-flute roughing end mill, I was going 1500 millimeters per minute at about 4 to 5 millimeters deep. And this was a full slot cut. Which brings me into the next part. Just a quick sidebar is, for me, instead of worrying about like dialing in feeds and speeds, worrying about how fast I was going, I just figured out the most aggressive cut I could make with my end mill with a full slot. And that was about 500 millimeters per flute, going around 10,000 RPM. I would alternate between 10 and 12,000 RPM and go about 3 to 5 millimeters deep at the max. And just with that simple formula, I was able to just mill anything I wanted with very little issues, very little noise. I didn't hear my spindle decreasing in strength. And the next thing that increased my tool paths was this. You can even go 4 flutes with a roughing end mill. And with this, I was going 2,000 or 2,000 millimeters per minute or 2 meters per minute. And that's how I got the operations to make one of these parts in under 30 minutes. And then that's 30 minutes, then flip, and then another 30 minutes, sometimes even 15, 20 minutes, depending on how complex the part was. And it was just a huge jump from using these super slow, tiny end mills, doing adaptive, and then changing up to doing traditional pocketing with these roughing end mills. And you actually can go too far with this, as I've learned. So I thought, I'm running 4 flutes. The internet says you can't run more than 3 flutes because of clearance, and I'll talk more about chip clearance later, but I bought one of these. It is a 6 flute 1/4 inch end mill, and you'll find that these are pretty hard to find on the internet. Not hard, but they're not very common. You don't really go past, you don't see many super high helix, high flute end mills for 1/4 inch. And that's because you need a lot of torque. If you're using a hobby machine, it's gonna stall out your motor, your spindle, which is what happened to me. And these also didn't have the serrations of a roughing end mill. And I did see some higher than 4 flute roughing end mills, but I didn't think it was worth it at that point. So you really just have to know the limits of your machine. The next thing is like, so here's some cool other lessons I learned along the way. This is a monocrystalline diamond. You may have seen a YouTube channel called Breaking Taps posting videos about this. These are absolutely worth the hype. They are pretty expensive, but the floor finish you'll get with this in aluminum is unparalleled. These things cut like a dream. They absolutely shred aluminum. These are super cool to use. So the last thing that was really impactful for my CNC milling was chip evacuation. It's a pseudo air curtain. It's not a real air curtain because I was too lazy to figure out how to get the air to flow perfectly in this Taurus. But it works pretty close. I was getting a bunch of chip collection, dust collection. So this side, from this tube, from my dust collector, it sucks the air in. And this tube is the exhaust of the dust collector. It blows air out. So this outer annulus blows air, and on the inside, it sucks the air in. So if I'm cutting, and I don't use a dust boot because I found that the bristles are annoying. Sometimes they get caught in the cutter. They have to be replaced. So I'll make my own boot. With this, if you're cutting like below the surface and your end mill is not too far out, then it's a wonderful air curtain. It blows it sucks all the chips, and it evacuates all the chips from the cutting area. It does blow some of the dust around, but looking at the bucket in my dust collector collecting, this works just fine. And yeah, those are all of my CNC tips that I can think of. The next thing is a random shout out to the place I work at, which is this software for CFD. Obviously, it's not a sponsor. It's just something I think you should check out if you are engineering and building stuff and you want to do CFD stuff for your toy projects. Check out Luminary Cloud. You can see here I'm rotating my bike around and getting some basic aerodynamic data from it. So that's pretty much it. I hope you found this CNC stuff useful, and hopefully you found this bike as cool as I do. So see y'all in the next video.